For a thousandth of a second, something out there releases more energy than the sun does in days. Then it vanishes. No warning, no echo, no repeat, usually. By the time the flash reaches Earth, it has already crossed billions of light-years of empty space, traveling since long before our planet had cities, or telescopes, or anyone to notice it arrive. And it lands in our antennas for an instant, so brief you could not perceive it, even if you were staring straight at the sky. So here is the question that astronomers have chased for almost 20 years, and still cannot fully answer. What is sending mysterious radio bursts across the universe? In 2007, an astronomer named Duncan Lorimer and his student, David Narkovich, were digging through 6-year-old data from the Parkes dish in Australia. They were not even looking for something new. They were combing old pulsar recordings, the kind of archival work that usually turns up nothing. And then, buried in the noise, there was a single spike, gone in milliseconds but far too bright and far too smeared to be anything nearby. It had punched through so much gas between galaxies that it could only have come from billions of light-years away. They called it a burst. The data had been sitting on a hard drive for 6 years. The universe, it turned out, had been flashing at us the whole time, and no one had looked. Here is the strange fingerprint that gives a fast radio burst away. The signal does not arrive all at once. It comes in smeared across frequencies. The high notes reach us first, and the low notes lag a beat behind. That delay is not random. It is the signature of a signal dragging its feet through the thin, invisible plasma that fills the space between galaxies. The more delay there is, the more cosmos the signal had to swim through to reach us, and so the farther away it began. When astronomers measured these delays, the numbers were enormous. These were not local accidents, not satellites, not lightning. These were messages from the deep cosmos, written in the bend of radio light itself. Then came the part that stops you cold. In that single millisecond, a fast radio burst can release as much energy as our sun pours out across several days. Think about that. Days of sunlight. Every photon the sun throws in every direction, compressed into a flash shorter than a heartbeat. The very first one, the Lorimer burst, was even more extreme. By some estimates, it matched what the sun emits over decades, all of it spent in less time than a single blink of your eye. Whatever makes these flashes is not gentle, and it is not subtle. It is one of the most violent, concentrated events we have ever figured out how to detect. For years, though, they stayed ghosts. Astronomers caught them only a few at a time. One here, one there, almost impossible to pin down, because the old telescopes saw only a narrow slice of sky. You had to be looking in exactly the right place at exactly the right instant. Then, in 2018, a strange-looking telescope in Canada came online. It is called CHIME, and it looks less like a dish and more like 4 enormous half-pipes lying open to the sky. It has no moving parts at all. Instead of pointing, it simply stares at half the sky at once and lets the planet's rotation sweep the heavens past it. Almost overnight, the count of known bursts jumped from around 100 to hundreds, and then into the thousands. The first CHIME catalogue alone held 536 of them. The rare flash had become a cosmic drumbeat, and then something broke the pattern entirely. One source flashed, and then it flashed again, and again. A burst named FRB 12102, first caught by the Great Arecibo Telescope, came back to the same patch of sky, over and over. That changed everything. It was proof that at least some of these sources survive whatever it is they do. Think about what that rules out. A one-time explosion, a star tearing itself apart, cannot happen twice. So a source that repeats cannot be destroying its own engine each time it fires. In a single discovery, the long list of wild suspects got dramatically shorter. And because it repeated, astronomers could finally do the one thing they had never managed before. They could wait for the next flash and trace it home. That source was tracked back to a small, faint, star-forming dwarf galaxy, roughly 2.5 billion light-years away. It was not a calm, settled place. It was a messy, energetic one, churning out new stars, exactly the kind of neighborhood where massive stars live fast and die violently, leaving behind dense, magnetic corpses. The address itself was a clue. The bursts were coming from a stellar graveyard. So what lives in a graveyard like that, capable of this kind of fury? The leading suspect is a magnetar. Picture a dead star, heavier than our sun, crushed by its own collapse into a ball barely the size of a city. A single spoonful of it would weigh as much as a mountain. Now wrap that city-sized corpse in the strongest magnetic field in the known universe, trillions of times stronger than the field of the earth beneath your feet. A magnetar's field is so violent that it could scramble the atoms in your body from thousands of miles away. If anything in nature can crack the sky open for a single millisecond, it is this. For years, that remained just a very good idea, a suspect with no alibi and no eyewitness. Then, on April 28th, 2020, the case got tested in our own backyard. A magnetar inside the Milky Way, a known object only about 30,000 light-years away, let out a radio burst bright enough to look like one of the distant ones. And we were watching. Two separate instruments, chime and stare. Two caught the same flash at the very same instant, and right alongside it came a burst of X-rays from the exact same object. That timing was the breakthrough everyone had been waiting for. For the first time ever, a fast radio burst was tied to a real, named, located object. And that object was a magnetar, sitting right here in our own galaxy. The burst was not as ferocious as the monsters from across the universe, dimmer by far, but it was unmistakably the same family of flash, coming from the same kind of star. After 13 years of theory, the prime suspect finally had a body at the scene. But a body is not a motive. Knowing that magnetars can do this does not tell us why a particular one fires when it does, or why some of them never seem to stop. So a team of researchers settled in to watch a single active repeater for nearly 20 months, using FAST, the enormous 500-meter dish nestled in the hills of southern China. They were not just counting bursts and tallying them up. They were watching something subtler. They were measuring how the signal itself twisted, how its radio waves rotated, as it left its source and crossed the space in between. In January of 2026, that patience finally paid off. The team caught a sudden, sharp change in the way the burst's radio waves were rotated, a spike that appeared and then faded away. The cleanest explanation was a cloud of magnetized plasma sweeping across the line of sight, dimming and twisting the signal as it passed. And the most natural source of that cloud was a coronal mass ejection, a violent belch of plasma thrown off by a companion star. In other words, the magnetar was not alone out there. It had a partner orbiting close beside it, and that partner had left its fingerprints all over the signal. That points us toward a surprisingly tidy picture. At least some fast radio bursts come from magnetars locked in binary systems, their flares shaped and disturbed by a nearby star. It is the strongest hint we have yet that these are not lonely monsters drifting alone in the dark, but partners, caught in a violent, intimate dance. The source type, after all these years, is finally coming into focus. We are learning where the gun is, and we are starting to see who is standing right next to it. And yet, even now, we still do not know exactly how the trigger gets pulled. Does the burst ignite inside the magnetar's own twisted, straining magnetic field? Or does it form much farther out, in a shock wave racing away from the star? Are the repeaters and the one-off bursts even the same kind of object at all? Or are we looking at two different species of flash and calling them by one name? Even the wildest old ideas, like cosmic strings, hypothetical leftover threads from the very birth of the universe, are no longer the front-runners. But they have not been completely ruled out either. What we can say honestly and clearly is this: the alien signal explanation simply does not fit the data we have. So here is the honest answer to the question we started with. We now know what is sending most of these bursts. Magnetars. Dead stars wrapped in monstrous magnetic fields, some of them locked in orbit with a companion star. That much is no longer a guess. But what we still do not know is the exact mechanism, the precise physics that pulls the trigger and lets the flash fly. And so, thousands of times a day, somewhere in the sky above you, something flashes brighter than an entire galaxy, and then goes completely silent. We have finally learned how to listen for it. We are still learning how to understand it. If you want the universe explained without the hype, what we actually know, what is still just theory, and what stays honestly unknown, this channel publishes the Honest Cosmos every week. Subscribe and stay curious. One question before you go. If we confirmed tomorrow that a fast radio burst was being deliberately aimed at us, would you want us to answer it? Tell me in the comments.